At the gateway of the Mediterranean, a 1.4-kilometer gap separates two worlds, yet a silent war rages beneath the surface. The Gibraltar span is not just a bridge, it is a geopolitical masterstroke, born from classified military dialogues and secret pacts. To plant a single pillar here, global powers had to trade more than just billions. They traded sovereign maritime control. The project represents the ultimate intersection of engineering audacity and elite-level military strategy in our modern era. Under the crushing pressure of 900 meters of seawater, the foundations must serve as fortresses for classified sensor arrays. Every ton of specialized concrete poured into the abyss was negotiated in windowless rooms by high-ranking defense officials. The sheer scale of the engineering required to bridge this strait is matched only by the intensity of the security protocols. We are looking at a cross-continental artery that doubles as the most sophisticated acoustic surveillance network on the planet. The process begins with the mass production of gravity-based structures, or GBS, massive concrete monoliths weighing 200,000 tons. A specialized ultra-high-pressure hydraulic press, the heart of the factory, shapes the dense, self-healing concrete modules. This machine exerts a force equivalent to the weight of a skyscraper to ensure zero porosity in the material. Engineers monitor the casting process with surgical precision, knowing a single micro-fissure could lead to a catastrophic structural failure. Inside these hollow concrete shells, technicians install miles of armored fiber optic cables for a private, unhackable military backbone. The logistics of moving these giants from the dry docks of Morocco to the exact GPS coordinates is an operation of its own. Each movement is shielded by naval escorts, ensuring the sensitive technology embedded within remains hidden from foreign intelligence. Deploying a 200,000-ton monolith requires more than just ballast. It demands a symphony of naval precision. The descent of a gravity-based structure to the seafloor is a point of no return for maritime architecture and security. Strategic sonar arrays, embedded within the concrete matrix, wake up as they reach the crushing depths of the strait. These sensors form a digital tripwire, capable of detecting the thermal signature of any vessel entering the Mediterranean. While the world sees a bridge for trade, military strategists see a permanent blockade-proof surveillance eye. The engineering core of the bridge rests on its ability to withstand the kinetic impact of a stray nuclear submarine. Massive passive hydraulic dampers are integrated into the pillar joints to absorb energy from extreme underwater shocks. Steel-reinforced carbon fiber cables, thicker than a human torso, are woven to hold the record-breaking 3-kilometer spans. Every cable strand is a data conduit, shielded by lead and titanium to prevent electromagnetic eavesdropping from satellites. Thermal expansion at these scales is a nightmare. The bridge must breathe up to 5 meters without losing its structural integrity. In the control rooms, AI-driven monitoring systems analyze stress load data in real time, scanning for microfissures in the alloy. The transition from African to European soil is bridged by an unseen layer of high-speed defense communication networks. Construction workers face the relentless Atlantic winds, operating robotic welders that never lose their 10-millimeter tolerance. Beneath the asphalt, hidden corridors allow for the rapid deployment of specialized rapid response security units. This is the Iron Diplomacy, a concrete manifestation of a truce signed in the shadows of global military command. The bridge spans are not merely held by cables, they are suspended by a lattice of high-tensile carbon steel weaves. Each main cable consists of 50,000 individual wires, each capable of supporting the weight of a heavy armored tank. A specialized robotic wrapping machine crawls along the primary suspension, binding the core with a weather-resistant polymer skin. This protective layer prevents the salt-laden Mediterranean mist from reaching the steel, eliminating the risk of catastrophic oxidation. At the anchorages, the tension is transferred into the bedrock using massive forged steel eye-bars embedded deep within the granite. The foundation pillars must account for tectonic shifts. The strait sits directly atop a major geological fault line. Seismic isolators consisting of alternating layers of rubber and lead allow the towers to sway without fracturing under pressure. Beneath the waterline, autonomous underwater vehicles, AUVs, scan the concrete base for microcracks. using high-frequency ultrasonic pulses. Data from these scans is relayed instantly to military servers, ensuring the structural integrity of the underwater sonar arrays. In the central pylon, a massive liquid-tuned mass damper counters the harmonic vibrations caused by extreme Atlantic wind gusts. The manufacturing of these dampers requires a precision casting process, usually reserved for nuclear reactor cooling systems. Every joint in the bridge deck is fitted with modular expansion plates, designed to slide seamlessly as temperatures fluctuate. Engineers monitor the stress loads of 30,000 sensors, creating a digital twin that predicts maintenance needs years in advance. Security is absolute. The bridge's internal service tunnels are monitored by thermal imaging and vibration-sensitive acoustic cables. This is a fortress disguised as a highway, a monumental achievement of industrial engineering and strategic military planning. The bridge deck is a masterclass in aerodynamic stability, shaped to neutralize the violent crosswinds of the Atlantic. Dual-wing profiles allow air to flow through the center, preventing the deadly harmonic resonance that plagues traditional spans. Engineers utilize wind tunnel data to calibrate the tension of every stay cable, down to the last newton of force. Beneath the surface, the concrete pylons are armored with a sacrificial layer of high-density ceramic-infused panels. These panels are designed to shatter upon impact, absorbing the kinetic energy of a rogue vessel or underwater drone. Logistics are managed by a private satellite constellation, tracking the movement of every supply ship with sub-meter accuracy. Heavy-lift cranes, anchored to the pylons, operate autonomously to hoist 500-ton steel segments into the sky. A robotic welding fleet then seals the seams using vacuum chamber technology to ensure zero hydrogen embrittlement. Inside the structural hollows, a labyrinth of nitrogen-cooled corridors houses the central nervous system of the sonar array. Every acoustic signature detected in the strait is cross-referenced with a classified database of global submarine silhouettes. To maintain this infrastructure, a permanent colony of maintenance robots crawls along the cables 24 hours a day. These units use ultrasonic sensors to detect internal corrosion invisible to the human eye or standard industrial cameras. Electricity for this massive complex is generated by subsea tidal turbines integrated into the base of the bridge pillars. This makes the Gibraltar span the world's first self-sustaining military-grade fortress powered entirely by the ocean's kinetic energy. Every bolt, every sensor, and every liter of fuel is accounted for in a closed-loop supply chain beyond public reach. Maintaining structural equilibrium in a 14-kilometer steel artery requires constant thermal regulation of the main suspension. Automated coolant sprayers, integrated into the cable saddles, activate when surface temperatures exceed 40 degrees Celsius. This prevents the molecular expansion of the steel wires, which could alter the bridge's tension and aerodynamic profile. Deep within the granite seabed, the anchorages are monitored by high-sensitivity tilt meters to detect any tectonic drift. Even a shift of 2 millimeters triggers an immediate recalibration of the hydraulic dampers at the tower base. The bridge deck is composed of modular orthotropic steel plates, laser-cut to a tolerance of 0.5 millimeters. These plates are stiffened by longitudinal ribs, providing maximum rigidity while minimizing the total dead load of the span. The assembly process uses a balanced cantilever method, where 2 cranes work in perfect synchronization from each tower. Failure to maintain weight symmetry during this phase would result in a catastrophic collapse of the vertical pylons. Military-grade encryption protects the data flow between the bridge's central AI and the remote maintenance drones. Every hour, a digital twin of the bridge is updated with real-time stress data from 30,000 sensors. Subsea cabling is protected by cast-iron articulated pipes designed to resist the impact of heavy-bottom trawl nets. A dedicated offshore substation converts the tidal energy into high-voltage direct current to power the internal defense hubs. This internal power grid is entirely isolated from the mainland, making it immune to external cyber attacks or blackouts. The logistics of this energy cycle are managed by a private cloud, overseen by naval engineers and data scientists. The bridge deck's wearing surface is not standard asphalt, but a specialized epoxy resin compound for extreme durability. This material is engineered to withstand the friction of 50,000 heavy logistics vehicles passing every single day. Beneath the surface, induction charging coils are embedded to power autonomous electric freight convoys in real time. This allows for a continuous flow of strategic supplies between continents without the need for traditional refueling stops. The bridge's structural health is maintained by a network of internal climate control units within the steel box girders. Dehumidifiers run constantly to keep the internal humidity below 40%, preventing any risk of hidden structural rust. Technicians perform manual inspections of the internal weld seams, using magnetic particle testing to ensure zero structural fatigue. High-altitude drones constantly patrol the suspension cables, using thermal cameras to detect any abnormal heat friction signatures. Any detected anomaly is instantly flagged to the bridge's central command, triggering an automated robotic repair sequence. The strategic importance of this artery necessitates a dedicated air defense perimeter integrated into the bridge's main towers. Phased array radar systems are concealed within the pylon caps, providing 360-degree surveillance of the entire strait. These systems are linked to the Naval Command, creating an impenetrable shield against aerial or missile-based threats. Under the sea, the bridge's base is surrounded by a ring of acoustic decoys to confuse hostile submarine sonar. The logistics of this underwater defense layer are managed by specialized naval divers and autonomous repair submersibles. Every component of the Gibraltar span is built for a 200-year service life under the most hostile conditions. The bridge towers function as vertical data silos, housing massive cooling fans for the subterranean server clusters. Exhaust vents, integrated into the pylon architecture, release heat from the defense network without affecting structural stability. Every 500 meters, an emergency response hub is equipped with automated fire suppression and medical trauma kits. Maintenance crews use specialized electric rail carts to navigate the internal service corridors within the main box girders. The steel used in these girders is infused with a corrosion-resistant alloy developed for deep space habitat modules. This material maintains its lattice integrity even when exposed to high salinity air for decades without a coating. High-tension bolts, secured by ultrasonic tensioning guns, ensure that no joint can loosen due to harmonic vibrations. A permanent fleet of autonomous marine drones patrols the waters around each pillar, scanning for explosive or sonar threats. The drone launch bays are hidden beneath the waterline, allowing for rapid and covert deployment during high alert status. Data from the sonar arrays is filtered by a localized neural network, eliminating background biological noise from whales. This allows the defense system to focus exclusively on the acoustic signatures of stealth propulsion submarine engines. Communication between the European and African terminals is redundant, using both buried fiber and high-frequency laser links. The laser arrays are mounted on the highest points of the pylons, ensuring line-of-sight transmission even in dense fog. Structural load-bearing tests are conducted monthly by driving heavy-laden train convoys across the specialized rail tracks. Every millimeter of deflection is recorded by the bridge's central brain, predicting the exact moment of material fatigue. The final phase of the Gibraltar span focuses on the integration of the automated traffic management and tactical defense AI. This central brain coordinates the movement of millions of tons of freight while maintaining a constant perimeter scan. Laser-guided docking systems at the bridge terminals ensure that intermodal cargo transfers occur with zero human intervention. Underneath the road deck, the carbon fiber tensioners undergo one final stress test, pulled to 90% of their breaking point. The results are verified by a team of structural analysts, confirming the bridge's ability to survive a magnitude 9 earthquake. As the sun sets over the strait, the bridge's low-energy LED security grid illuminates, visible from space as a golden thread. This lighting is not for aesthetics. It provides the precise frequency needed for the bridge's optical tracking cameras. The sheer audacity of this project has redefined the limits of what civil engineering can achieve in hostile maritime environments. It stands as a testament to the secret negotiations that prioritize global stability over regional territorial disputes. The Gibraltar span is no longer a blueprint. It is a functioning organ of the world's new industrial and military heart. Billions of dollars, years of classified labor, and the friction of two continents have culminated in this single steel line. Behind every vehicle crossing this bridge is a complex layer of defense technology, protecting the future of global logistics. We have witnessed the birth of a new era, where the physical and digital defenses of a nation are inseparable from its infrastructure. The engineering might of the 21st century has finally conquered the ancient divide between Europe and Africa.